Hello grade 11s, welcome to my channel and hopefully you're going to learn something. So today we're going to look at this physical science paper 1 written June 2023 in the EC. This is important especially for you guys looking to do well in your final exams, because this material is examinable in your finals and essentially going to be examinable in your matric examinations. So this gives you a good shot at getting the best mark at the end of this year so that you can apply for your chosen career, and secondly to prepare for your grade 12, because most of the questions here you will meet again in your grade 12. Now let's start with the instructions. We know clearly that we prefer the operational instructions. The rest are pretty easy to deal with. So formulae and substitutions must be shown in all calculations. The rounding off, it is a minimum of 2 decimal places. So this clearly says 2 or more decimals are acceptable. And then if you're given an opportunity to give explanations, you can absolutely use anything that is applicable, but keep it brief, all right? That's it. So let's go on to question 1.1. Technically, this is the MCQs, you already know, but please read the instructions. It says 4 questions are provided as possible answers to the following questions. Each question has only one correct answer. Choose the answer and write only the letter A to D next to the question number. And we are given an instruction as to how to go about doing that. Now let's start. 1.1 says, which one of the following is an example of scalar quantity? Now we know that scalar quantities basically only has magnitude. Okay, they only have size basically. So only mass is a scalar quantity, because velocity is a vector quantity. It has both magnitude and direction. Acceleration is a vector quantity. It has both magnitude and direction. A force is a vector quantity. It has both magnitude and direction. 1.2 says the frictional force acting on a sliding object. So we're talking about frictional force acting on a sliding object. So let's draw our object. There is our object on a surface. Okay, so we've got frictional force going in the opposite direction. So if it is a moving object, we call it Fk, right? And then of course there would have been a force that is responsible for that object to slide in the opposite direction. Okay, so it says now this frictional force acting on a sliding object by the surface in contact with it depends on, so this simply says, what do we know? We know that Fk is going to be equal to mu k times the normal force. So does it depend on air resistance? The answer is no. Does it depend on the normal force? Yes, because we can see that the normal force is part and parcel of how we calculate our frictional force. Does it depend on the area? The answer is not the area, but the type of surface. It does not depend on the type. Technically, it actually does. So because it says it does not, then we cancel that out. So the answer becomes B. All right, so a satellite orbits Earth at a height where the gravitational force is a quarter of the force experienced on the surface of the Earth. Okay, if the radius of the Earth is r, the height of the satellite above the surface, so we want this height above the surface of the Earth is, if I get a quarter, I already know that the answer should be C. But how will you know if you don't know like I do? Now we think about it. We're going to say there is the surface of the Earth, there is the center, we've got the radius r. Okay, if the satellite were to be here on the surface, okay, we know that the force of gravitational attraction between the two would be G m Earth times m of this satellite multiplied by r squared. That is the definition of our Fg. if this satellite was to be on the surface. But now there's our satellite orbiting in some silly area, so there's a lot of things going on there. So now, what is that height? That's the question. Okay, but all we know is that that is the story, such that the distance between the center of that satellite and the center of the Earth is basically h plus r. So we want to work out h. So now we know that we are told that we have a quarter of g, of fg. A quarter of fg is basically a quarter of g m Earth m satellite divide by r squared. Okay, that is what happens. Okay, we're simply multiplying that by a quarter. And then we go on and say, fine, if we cannot cancel things out, we simply multiply the numerator. So it still remains g m Earth m satellite divide by this one becomes 4r squared. Okay, now what can we do here? We're going to have g m Earth m satellite divide by 4 is basically 2 squared times r squared. Okay, so we can factorize this thing again, or using our exponential rules to sort it out. So if these are like that, they carry the same exponent, we can simply say 2r squared. Okay, great. So what do we know, guys? We know technically that this guy right here is what would have been the distance between the center of the Earth and the center of that satellite. So in effect, this implies that h plus r must give us 2r, okay? Because we're not worried about the square now. Then we work it out and say this implies that h is going to be 2r minus r. Therefore, our h is going to be basically r. So please, guys, know how to work these things out. Sometimes these questions are the type of questions that are not so easy to deal with. You've got to know how to work your magic. Again, make sure you can apply your maths gymnastics here. Next question says, state Coulomb's law states that the magnitude, so it looks like that guy doesn't, nope, that guy doesn't come in. So Coulomb's law states that the magnitude of the electrostatic force exerted by 2-point charges Q1 and Q2 on each other is directly proportional to the product of the magnitudes of the charges and inversely proportional to the square of the distance between them. True. Now it says, which of the following graphs best describe the relationship between the electrostatic force and the inverse of the distance between the two charges? Obviously, we know this is coming from Coulomb's law, that the electrostatic force is equal to the constant K times Q1 times Q2 over R squared. Now from this one, we know that Fe is basically directly proportional to the inverse of the square of that distance between them, right? Because we are looking at this as a whole now. That's why we call it the inverse. So if this increases, the force increases. We're not comparing F and R squared, but the entire inverse. So we expect a direct proportionality, because now this is a direct proportionality, which makes that answer C, because it has to be the positive gradient passing through the origin. Okay, that's it. So if you know these things, you don't struggle at all. Now in the diagram below, a bar magnet is being pushed into a coil, right? The current induced in the coil is in the direction indicated. Where is that? We can see that the galvanometer or any current detector will give a deflection in which the current is passing. And obviously, if it goes to the right, it means the current is going to the right, like that, okay? So as we follow this current, it's going to be climbing on this segment of our coil, or solenoid, if you will. So the current is doing those things, all right? And then it's coming down here, all right? So that's what we've got. So we use our right hand solenoid rule here to determine things, okay? Great, it's applicable. So let's read further. Which one of the following combinations correctly shows the polarity of the end of the coil? Okay, so we want to know, is it south or north, okay, of the bar magnet as the bar magnet approaches the coil, and which end of the bar magnet is approaching the coil, okay? So that's the question. We want to know this end of the bar magnet and that end of the coil in terms of polarity. Now, as we said, we're going to use our right hand solenoid rule. So you're going to put out your hand in front of you. Okay, there's your hand. It's not really looking great. But anyway, the fingers are not equal. So this hand is facing the other way around. So the palm is on the other end. So these are your knuckles, right? Right, so your hand is out like that. So basically, we know that the direction of the fingers points to the current. Okay, maybe let me write a bit better. Okay, this points in the direction of the current, the fingers. And then the thumb points in the direction of the North Pole. Okay, so essentially, if we place our hand, because we can see that on this end, this side, the current is going up, so it's in the direction of the fingers. So that means the thumb will be pointing to that side. So this means this becomes the north. And then what we were asking ourselves what it is the South Pole. Okay, great. And then if that is the South Pole, it will always try to oppose the magnet as it is approaching, then making it the South Pole as well. Okay, so that means it's going to be south. Great, not a problem. So you see, this is very easy. So the polarity of the coil facing the bar magnet is going to be the South Pole, right? Right. And then the end of the bar magnet approaching the coil, we could see here that it's South Pole. Okay, now what is the answer? The one that ticks all the boxes, because that is wrong, that is wrong, that is wrong, that is wrong. So the one that ticks all of them boxes is B. Okay, great stuff. So please take note of questions like this. They will horrify you if you're not ready, right? Great. Let's do the last question here. It says now 2 bulbs, A is marked 500 watts and B 200 watt, in fact it's watt, are both rated to function at the voltage of 250 volts. Okay, what is the ratio of the resistances? But of course, remember, the higher the power, the lower is the resistance. And then the lower is the power. What did I do here? Should be the opposite thing here. Then the lower the power, it means the higher is the resistance. Great, because this is all related to current. But what do we know? We know that P is equal to VI. This is now the generic thing is, as you can see, if there's a higher current, there's going to be a higher power. Less current, there's going to be a business. But the most likely in this case is going to be the V squared over R. Still the same thing. Look, if the denominator is great, that one becomes less. If the denominator is small, that one becomes more. So even though you may adapt this to this one, you would still come to a similar effect. Okay, so please know what is going on in here. So we are saying now, what is the ratio of the resistance RA over RB. Okay, so we're fine. So we know that technically, if we solve for R there, we know that RA is going to be power, no, not power, sorry, is going to be V squared over power, right? Because if we use that equation, we will be able to see that that is the story that we need to do, as well as RB is going to be the same thing. It's going to be V squared over power for that. Okay, now let's do this calculation right here. So we know that RA is going to be V squared, which is 2, it's 250 squared over, now we're dividing by the power, that is the power, so we're dividing that by that of RB. The resistance is going to be 250 squared over 200. And then you know that if you're doing that, in fact, we can even say equal sign. So we know that this is 250 squared divide by 500. Then we flip this, it's 200 over 250 squared. Now with this setup, we know that this guy does the number to that, then these two do a number to that. So our resulting business here is going to be 2 over 5, which when you express in the other way around is going to be 2:5. Obviously, we saw that the lesser resistance will have a higher power. The greater resistance will have a lower power. So they are in that ratio 2:5. Now that becomes D. Again, it's one of those questions you want to watch out because they're indirect and therefore they demand a little bit more from a student. Okay, let's move on to question 2. Now we're going to start doing some serious work. Now, we are told here a box of weight, so we're given the weight 55 newtons, is suspended from a ceiling by a string. Now, a horizontal force F is then applied to the box to keep it in equilibrium, so it becomes an equilibriant. Okay, when the string makes an angle of 30 degrees with the ceiling, okay, the tension on the string is T. Great. So if this is in equilibrium, it means that box is stationary there, it's not moving. So what do we know? Well, we know that the weight is directed straight down. Okay, and then we can use Fg for the weight. Right. So those are the forces. So we've got the tension in that direction, we've got the force of gravity down, we've got that force horizontally to the left, and that means the angle between these two is going to be 90 degrees. Okay, all right. So it says now what is meant if the box is in equilibrium. Okay, great. What we know is that to answer 2.1, we know that the resultant force acting on the box is 0. Okay, basically that means there's no resultant force acting on the block. So we get your first 2 marks then, nice and easy. 2.2, it says draw a closed vector diagram of the 3 forces: tension, force, and weight, or they used a small letter W for the weight, so we can do that, not a problem. By using a tail to head method, so they're already telling us what is going on, and then says clearly label the 3 forces and the relevant angle. Okay, great. So how do we do that? So what I like to do is to shift forces. So since I know the weight is appearing here, I can actually shift it to appear on this side. Okay, so I've got my weight going down like that, and then I will shift that force to here from that corner to that end. So this is our force F. And we know that the direction, the angle between the force and the weight was 90 degrees. So it remains as 90 degrees. So essentially, we've got our closed triangle that shows our forces are in equilibrium because the arrows are going in different directions. So that's what we want to draw. Very easy, eh? Very easy. So we've got ourselves a very nice one. A very nice one. Okay. Nice and easy. So we know that the weight is directed down. So this is our weight, which is 55 newtons. They gave it to us. We can write it down. And then we know that we've got our angle here of 90 degrees, but we really need to show it, maybe. And then we know that that angle between the tension and the horizontal was 30 degrees, and the tension is going in that direction. So that is the tension, capital letter T, and the force was headed in that direction. So that is the force F. So we are done. So we've shown a relevant angle. We have labeled the forces acting and the entire structure, the way it looks. So that's how we score those 3 marks. Okay, easy. Easy, 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 easy. 2.3 says, calculate the magnitudes. So the question says magnitude. So direction is not a necessity. But I always treat vectors with some respect. So you can decide. So let's do the first one, F. So in that triangle, F is adjacent. Can you see? Is adjacent. And we can see that what we know the value of is opposite, right? So we can see that if we want F, we know the opposite, we want the adjacent, that is 1030. What happened here? 1030 degrees is going to be the weight, which is the opposite side over F. Okay, great stuff. So we can say, therefore, our F here is going to be our weight, which is 55, divided by 10 of 30 degrees. So let's do the answer there. Nice and easy. There's the calculator. So we've got 55 divided by 1030. So wait a minute, 55 divided by 10 of 30 degrees. So this is now 95,26 newtons. Sorry. Okay, that is 55,96 newtons. And then of course we can see that the direction of that force is westwards. So westwards is basically at 270 degrees, right? Because we always use the compass like this. North is at 0 degrees. And then south is at 180 degrees. Okay, we always go clockwise with our angles when we are doing the bearing. Okay, so that means to the west is at 270 degrees. So you can write west or 270 degrees, but I'm putting it in brackets because the direction was not really a necessity. But for me, trying not to cheat myself when it comes to vectors, because there's a time when questions are not that direct and then you miss the direction, then you lose unnecessary marks. Okay, most likely substitution and answer, excluding the direction because that was not the requirement. Okay, so let's do the tension. So tension is on the hypotenuse side. Okay, the hypotenuse side and the opposite side we know. So we know that that is sine 30. So sine 30 degrees is going to be the weight over the tension, right? Therefore, we know that the tension, because that's what we want, is going to be the weight, which is 55 divided by sine 30 degrees, which is a half, okay? That means it's going to be 110, yeah? Because it's just the same as 55 by 2, so that becomes 110 newtons. But remember, the tension is at 30 degrees to the west. Remember, the tension's direction is here, is like that. So the horizontal here is at 90 degrees. So basically we are adding 30, because remember, vertically opposite angles, if you've got 30 there, there's going to be 30 on the other side. So we can decide that clockwise, that would be at 60 degrees. Okay, if we calculate that angle, we know that is 30, therefore that should be 60 degrees. Or you can say that is 30 degrees north of east. Again, it's not a necessity, so don't break your head, but get into the habit of always knowing what your direction is. Okay, again, substitution, and the answer should be fine. So we take our 9 marks with a big smile on our face, and we move on. So let's get to question 3. Now question 3 says, a car with a mass of 350 kgs is accelerated up along a straight hill by a net force. Okay, that means the resultant force. Okay, so this is a net force of 370 newtons. Now the net force is parallel to the hill, so we can see that this is the resultant force. So we've got the resultant force of 370 newtons. Okay. Anyway, it says now which makes the angle of 35 degrees. So there's the angle we can see with the horizontal, and then we're given the coefficient of kinetic friction is 0.21. Okay, so that means there's going to be friction here as well. Okay, now it says draw a free body diagram with labels of all the forces acting on the car. Remember, this is just the resultant force. Okay, so this is just the resultant force, so it doesn't show all the forces. But now when it says all the forces, it means you're going to do the reverse. You want to show the rest of the forces that are acting on that car. Obviously, we know that there's going to be an applied force, which is supposedly going to be greater than the resultant force. Maybe let's make it look like that. So there's going to be an applied force. We always call it an FA. Then there's going to be friction opposing the direction of motion. We call it Fk because it's a moving object. We know that this object will have weight straight down. We sometimes call it Fg or W. And then there's going to always be a normal force by the surface on the car. Okay, so we can see there's 4 forces right there. So we start question 3. Okay, so 3.1. We know that we've got our lovely little thingy there, so we want all the forces, not the resultant force. So we've got our force applied, which is probably the engine of the car, and then we've got our frictional force here, which is Fk. That's an acceptable label. Then we're going to have ourselves our weight straight down. We can call it Fg, force of gravity. And we're going to have our normal force acting perpendicular to the surface. So a capital letter N is acceptable. So make sure all of these things make contact. with the stuff. So that is the 4 marks, guys. Easy. But you're not really, for me, I feel like the examiners are not exactly fair to dictate what labels you must put, because I mean, come on, man. You know that there's lots of teachers who teach differently, the textbooks write differently. These exam guidelines are purely just guidelines, not rules. But the way they are treated is as if they are the rules. They're dictating this is the only thing you should do. If that is the case, I would rather they say these are exam rules, okay? Because to say guidelines and then force people to regurgitate those things is ridiculous. But anyway, I'm not the examiner, so don't learn anything from me in that regard. But yeah, I feel that is just a weak point of our curriculums in the country. But anyway, so for me, even if you wrote anything that you chose, if then you wrote something that is not recognizable, that is what I should expect them to be, a little bit flexible. If you write something that is not usual, then you put a key and explain what is what, and that should be enough for me, than to say you're going to be penalized if you used different, symbols. Who said that is standard? That is not a standard. It is basically a mere suggestion. Anyway, let's not talk too much. Don't be misled by me, guys. Listen more to your teachers than to me. But just look at the work I am doing and perhaps compare and contrast with what you've been taught. Now it says calculate the magnitude. Again, direction here is not being dictated. So if you add it for a vector, it's okay, but it's not mandatory. The acceleration of the car. So we know that this car, if we were to just draw a nice diagram here, a force diagram, we know that the resultant force acting on it is 370 newtons, okay? Now we can simply say to the west. Of course, that is basically the story that we were given. Now this is when we forget about all the other forces, because the resultant of all those forces acting together would be that resultant force. So Newton's second law will tell us that we've got our resultant force giving us MA. This implies that 370 newtons, oops, not degrees, is equal to the mass of this object was 350 times A, okay? Therefore, our A is going to be 370 divided by 350. Okay, so let's do this. So this is 370 divided by 350. So I'm getting a 1,0, say 2 decimal places, 0.6 meters per second squared. But now this is acceleration. Remember the incline. We always use the north to south business. So this is 0 degrees, right? And then we've got east, which is at 90 degrees, right? And then we've got south, which is at 180 degrees. Then we've got west. We've got west, which is at 270 degrees. Okay, so we're going clockwise. So as you can see, this is 35 degrees north of west. So this basically says we can just say 270 plus 35. It gives us 305. So this is at 305 degrees. Of course, I'm putting it in brackets because it was not really a necessity. Or someone can say this is basically 35 degrees north of west. Okay. Now 3 marks is formula, substitution, and the answer for the magnitude only. So 3.2.2 says the force of friction on the car. So usually when you see 4 marks, it says perhaps 2 steps. So how will we get the frictional force on the car? The key to that business is the normal force, right? Because we don't know the force applied. So if we get the normal force, we will be home free. But how do we get the normal force? By looking at the components of weight. So the weight will have an FG perpendicular, and then it will also have an FG parallel. We know these ones are perpendicular components of the weight, meaning they are perpendicular to each other. So we've got FG parallel, downslope. Okay, so we need to find FG perpendicular, because FG perpendicular is perfectly balanced with the normal force. So all we can simply say is that the normal force is equal to FG perpendicular. Okay, and then you can just say the perpendicular forces are in balance, or they are balanced. Maybe let's just say that they are balanced, because the object is not dipping into the surface or being lifted off the surface. So sometimes finding smart ways to answer your question. Now we know that FG perpendicular is essentially the cosine, because remember this angle here is going to be that angle in that corner. All right, so maybe let's just use the little highlight. So this 30 degrees would actually be here. 35 will also be there in our diagram. So we know that, look, if we want the FG perpendicular, we simply say cos, because we know the weight, or FG. So we will simply say this is cos of 35. So basically this tells us that mg cos 35 degrees represents our FG perpendicular. This basically says we've got 350 times 9,8 times cos of 35 degrees. So let's start. So cos 35, then we multiply by 9,8, then we multiply by 350. So we get a very big force here, which is 2809, comma 6 9 to 2 decimal places. Maybe let's make it 392 newtons, because it's an intermediate step, so don't round off to 2 already. Okay, we can say then we know that the frictional force, the kinetic friction in this case, is going to be mu k times the normal force. Now we were told this is 0,21. Now we just calculated this one. Let's see. So 0,21 into 2809,692 gives us a 590,04 newtons. Now we can round off to 2 decimal places. But now, in what direction is the frictional force? Remember, it's the same story. It's going like that down. So that means this angle is 35 degrees. So we just add 35 to 90. So 90 plus 35 gives us 125 degrees. Okay, or you can say 35 degrees south of east. Okay, so that is the story. So always try to get the direction right. So you can see here 2 steps, right? Most likely whatever you had to do here, the substitution is the most important, but that answer was intermediate. Where it comes into effect is the formula, the substitution, and the answer for the magnitude. Okay, easy. We move on. So 3.2.3, it says now the force applied on the car. So we want this guy. Now for us to do that, we need all the horizontal forces. So that means we need our FG parallel. We know the friction. Then we just will be able to work out the business. So let's start here. we know that FG parallel. Okay, maybe let's start by drawing our diagram nice and easy. So our diagram, remember this one is going to be going to the west, but it's not really going to the west. We're just simplifying our work. So FA is against two forces, which is FG parallel and the frictional force. Okay, always have a diagram in mind of what you need to work out. Okay, so always have this in mind. And then now what we know that we need to know this dude, because this one we already know. Okay, once we know these two forces, there will only be one unknown. So we can just simply say FG parallel. Do we really want to exclude it from this calculation? I don't think we need to. So we can just say the resultant force is going to be basically FA. Maybe let's start it this way. We know that from Newton's second law that the resultant force is equal to MA, right? Right. Which implies that it's going to be F. Okay, we can choose to this side as positive, to the left as positive, or upslope as positive. So this is going to be FA minus FK minus FG parallel equals, now this is the resultant force. Okay, because that's what they gave us, right? Right. You can write MA if you like, doesn't matter. So this implies that we've got FA, which we don't know, minus, now we calculated our frictional force, it became 590,04, minus FG parallel is going to be mass, which is 350 into 9,8. Now remember that one will be the sine of theta, which is 35 degrees, equals, we were told this is 370. Okay, not a problem, not a problem. Maybe we can just decide we leave this one alone and say MA just not to flip-flop. Okay, therefore we can tell that our applied force is going to be 370 plus 590,04 plus 350 into 9,8 times sine of 35 degrees. So let's finish up here quickly. So we've got 370 plus 590,04 plus 350 into 9,8 into sine of 35. So I'm getting a 2927,41 newtons. And then that applied force is at the same direction as that resultant force. So that is going to be at 200 and, what did we get? 305, yeah. At 305 degrees, because it's that same direction right there. Okay, so that's it, guys. That's the answer. So I won't be able to underline it because I kind of squashed things. And you can see that this is greater than our resultant force. Yebo, yes. Yebo, yes. Okay. Great, so what do we do now? We're only getting 3 marks. Okay. So I think this calculation was important because we didn't know. And then the rest of the substitutions, because we already knew those ones. And the final answer. And that's how we take our 14 marks with a big smile. Okay. Okay, let's move on to question 4. Okay, question 4. You should be familiar with these types of questions, especially with this type of diagram. you will always be humbled by these kinds of questions in your metric here. Now 10 kg block, so we've got our mass. A 10 kg block is resting on a rough, now once it is rough horizontal surface, we know there's going to be friction. So if it is resting, what we have is static friction, right? Is connected to block of 15 kgs by light. If it is light, it means no weight is added. If it is inextensible, it means if there's a movement, the whole blocks move at the same rate, okay? So no forces get dissipated by that string. Okay, moving over a frictionless pulley. Even the frictionless pulley simply says, if one has got tension on this side, it should be the same as on the other side. Okay, great. Now due to the weight acting on a 15 kg block, the block of mass 10 kg started to move to the right. So the direction of motion is like this. Okay. Now a force F is applied to a 10 kg block such that the system moves at constant. Now that is a big statement. If we're moving at a constant speed, that means the forces are effectively balanced. So the resultant force on the system is 0. So with that resultant force of 0, it means there's a lot of equalities. But now what is the driving force here? If we focus on this guy, if we focus on this guy, we will know that we've got tension going in that direction, and then we've got our gravitational force going in that direction. So this is Fg, which is going to be 15 times 9,8, right? And then we've got our tension going up in there. But if this is doing constant velocity, it means these two are equal. Okay? So these are some of the things you want to make sure you understand, because the resultant force acting on that 15 kg block should be 0. And if it is so, that means those two are equal. So with that story being said, what must we do? Well, I told you the angle between the applied force and the horizontal is 25 degrees. But for this one, note something. If that force is acting at an angle, it will divide into its perpendicular components, right? Because they are perpendicular to each other. So that is going to be the force, which is the horizontal component of that force. And then we're going to have the vertical component of that force. These are things you want to make sure are in order, because the actual force that is acting on the system is the horizontal part. And then if we focus on this 10 kg block, it's going to have its weight straight down, which is Fg, and then it's going to have its normal force up. Okay? But now you see the forces acting on this block, the vertical ones above the surface, is going to be the normal force and the vertical component of that force F, okay? Because when that force is at an angle, it is acting through its components, okay? So now, once we've done that, we are sorted, because here we also know that the weight is basically doing its things down, okay? So once we work out things like that, we can move on. Now, the frictional force acting on the 10 kg block is 8 newtons, okay? Great, so we can add it. Say there's our Fk. Okay, is there. All right. Now it says state Newton's second law of motion in words, okay? That is basically textbook work, guys. Easy stuff, easy stuff. So this one, we say a resultant force applied on an object will cause the object to accelerate in the direction of the resultant force, such that the acceleration is directly proportional to the resultant force, and inversely proportional to the mass of the object. So that's a bit of a paragraph, you know. So I kind of had to pause because it's going to chow our time. So let's go on. Easy, 2 marks there. There's no need to miss it. Write the net force acting on the system. We know that it is 0, right? Because we're told we're doing constant velocity or constant speed. So easy, 1 mark. So 4.3, okay, divided into 4.3.1. We're told to calculate the magnitude, okay? That means, again, if you include direction, it's out of your, whatever. But do it. The tension on a 15 kg block. See, it's 2 marks. It's very easy. So we know that, well, if we choose down as positive, for example, maybe let's choose up as positive. I don't know. So we can simply say, with up chosen as positive on that object, we will know that the resultant force F res is equal to ma. Okay, we're using Newton's second law. This means up is positive, tension minus Fg is going to be equal to ma. Okay, this implies that tension minus Fg is basically mass times 9,8, which is going to be equal to 15 into 0 because we're doing 0 acceleration. We can say, therefore, our tension is basically 15 into 9,8. Okay, so let's do it quickly. 15 into 9,8 is 147 newtons. Now on this block, the tension is upward, or you can say 0 degrees. So sometimes we can use an arrow to indicate the direction, but it's not a necessity here. So what matters here is essentially the substitutions and the answer, okay? Because it's pretty straightforward. So 4.3.2 says the force applied. Now that's a bit of work. 4 marks already says 2 steps are more likely to be done. So what do we need here? We need this 10 kg block because we've got tension in that direction, which we just calculated is 147, and then we're going to have this force acting through its components, which we know that we're going to have them like that. So the answer is that these are perpendicular, so this is Fy and that is Fx, and that angle is 25 degrees. Okay, so what we need to find Fx, because that can help us to find F. Okay, easy stuff. So let's go on. To answer this question, we know that here the resultant force is equal to ma. All right, this implies, now we're moving to the right, the tension is bigger, so tension minus the horizontal forces here is basically, oh, we forgot another force here. There's another force here, the frictional force. So we forgot. So here we're going to have tension minus Fk minus Fx is equal to ma. So that is the most important, because we want to use our Fx as a means to an end. This implies that 147 minus, we're told this is 8, minus Fx. By looking at that triangle, Fx is basically cos of theta, so it's going to be basically F times cos of 25 degrees, because cos is going to be fx over hypotenuse, which is f. So when we work out fx across multiply, that's what we're going to have. So this is equal to the mass of the 10 kg block. Remember, this is the 10 kg. So this is going to be 10 into 0 because we don't have that business there. So this implies if we transpose this guy to the other side and rearrange, we know that our F is going to be equal to 147 minus 8 divided by cos of 25 degrees. So these gymnastics, guys, are very important. So I'm moving a bit quicker so that we can save a bit of time. Okay, so we've got 147 minus 8 divided by cos of 25 degrees. So this gives us a 153,37 newtons. Okay, to 2 decimal places. But now in what direction? Remember, again, if you're looking at our direction, this is north, east, south, west. So this is going at 25 degrees in that direction. So that is going to be 270 plus 25, which is 295. Again, that was not the question. The question was on the magnitude. Okay, easy stuff. So what do we do here? 4 marks. Basically, I don't know if we're going to get the mark for that, but I doubt. Let's just say the mark here is for the general substitution in this particular determination, right? And then the answer, 3 marks. Ha. Okay, right. Maybe we should, because there's 4 marks in there. It's fine. Let's include it, but it's a very weak one. It's a very weak one. So we move on. But I don't think the formula is correct though. Maybe we can just say this left-hand substitution rather. The formula, we've used it in the sub-question above, so we can't get marks for it again. But we didn't get a mark for the formula. So, well, it depends on what the official marking guidelines are saying. So let's move on. It says now calculate the coefficient of kinetic frictional force acting on the 10 kg block. Now that means we need to know the normal force here. And for us to know the normal force, we need to do some gymnastics, right? So 4.3.3. We know for a fact that the vertical forces are in this manner. We know that F res is equal to MA, right? For the 10 kg block. So the 10 kg block has got its weight down, and then it has got the normal force up, and then it's got the vertical component of that force. Okay, so always have a diagram that you are using as your reference diagram. So here we can clearly see that. Fine, we can simply say FG minus Fy minus N is equal to MA, right? Now let's do this. Fg is basically 10 into 9,8, okay? Minus Fy is basically F sine theta. That F sine theta, what did we find? It's 153,37 into sine of 25 degrees, right? Right. Minus N is equal to 10 into 0 because there's no acceleration in the vertical direction. So it's a bit of a silly calculation, I'm telling you. And then what does this imply? This implies if we transpose N is basically going to be 10 into 9,8 minus 153,37 into sine of 25 degrees. Okay, we needed the normal force. Now let's see. So this is 10 into 9,8. That's 98. Minus 153,37 into sine of 25 degrees. So this gives us a 33,18 newtons. Okay, maybe let's say 183 because it's an intermediate step. Okay, now to seal this, we can say then we know that Fk is going to be mu k times the normal force. This implies that Fk, we were told, is 8 equals mu k, which is what we want, into 33,183. Can say therefore our coefficient of kinetic friction is going to be 8 over 33,183. Okay, 8 divided by 33,183. Then it gives us a 0,24 to 2 decimal places. Remember, this one does not have a unit. So that's it. Great stuff. So again, you could see here 2 steps were necessary. So essentially, what matters the most here? I would believe, without a shadow of a doubt, that this calculation is important, right? And the rest of the substitution. In fact, even Fg, we did not calculate here, so sometimes that is good enough. The rest is really history, and then we can say formula, substitution, and answer. 4 marks. The rest is really, you know. So we take our 13 marks with a big smile. Next question. Okay, so we've got question 5. So question 5 says a satellite of mass 380 kgs, okay, in a circular orbit at a certain height above the surface of the Earth. The Earth exerts a gravitational force of 2,65 times 10 to the 3 newtons on the satellite to keep it in its orbit. Now state Newton's law of universal gravitation in words. Again, textbook work, guys. So to do 5 point. All right, so again, something that you should already know, nice and easy. So it says every particle in the universe exerts a force of attraction to every other particle such that the force is directly proportional to the product of their masses and inversely proportional to the square of the distance between them, or sometimes they use the word centers, okay, which is not a big deal. So let's deal with 5.2. It says now calculate the height in kilometers of the satellite above the surface of the Earth. So this is the same question as the one in the MCQs. So we've got our radius of the Earth here, and then we've got our satellite with all its things somewhere there. So we've got our height here that we want. So the distance is basically h plus r, okay, and we want h. Easy stuff. So we're going to say find the gravitational force of attraction is going to be the big G, big M, small m for the satellite. Now in terms of r, okay, we can just write here the formula as it appears, r squared, okay. Now this implies we substitute, this is 2,65 times 10 cubed. All right, is equal to G is 6,67 times 10 to the minus 11, right? Right, but let's just double check. Sometimes it's easy to mess it up. So there are our constants here. It's 6,67 times 10 to the 11. And then the mass of the Earth is 5,98 times 10 to the 24. Okay, and then the mass of this one was already 3.8, né? This is divided by, now we want the radius of the earth. So the radius of the earth is 6.38 times 10 to the 6, and then plus h, and then we're squaring that. Okay, great. So I hope everything is where it's supposed to be. Oops, not you. All right, let's quickly finish the business here. So it says in kilometers. Wow, careful there, careful there. Read the questions properly, né? I almost made a meal. Okay, this is basically over 1, and then we do our gymnastics, which will eventually tell us that our 6.38 times 10 to the 6 plus h squared is basically equal to, now what do? We just leave this one. Okay, so that's what we've got. Easy, né? And then of course we will divide by that force here. Now here we can do our fancy gymnastics. Take the square root. What we do on the left hand side, we must do on the right hand side. Okay, so this implies that our 6.38 times 10 to the 6 plus h is going to be whatever we get. So now let's just do it. So this is 6.67 times 10 to the minus 11 into 5.98 times 10 to the 24 times 380, divide by 2.65 times 10 to the 3. Okay, so here make sure you substitute it correctly, guys. It can be a nightmare. So I'm getting 7562795,729. Okay, and then of course we can see here that therefore our h is going to be this number, 729 minus that one, 6.38 times 10 to the 6. Okay, but now they said in kilometers. Remember, this whole thing is in meters. Okay, so then we're going to divide this whole shenanigan by kilometers, which is 8,000, because this is going to be in meters. So we're going to say minus 6.38 times 10 to the to the 6. It gives us what it gives us, and then we divide by 8,000 to get kilometers. So I'm getting 1182.80 to 2 decimal places. Okay, this is now kilometers, because we were told to do this in kilometers. But if we didn't want to, we know that this is all in meters. So great stuff. Now that's it. Easy. Let's see, 5 marks. Okay, formula. Great. Substitutions in general, but this one here, it's a calculation on its own. 3 marks. And this division by 1,000 is the 4th mark, and then the answer is the 5th mark. Okay, so we're taking these 7 marks with a big smile, and we move on. Okay, so let's get to question 6. So question 6 says a class of grade 11 learners wanted to investigate the relationship between the inverse of an electrostatic force and the distance between the two identical charges. So the word is identical. They carried their experiment and recorded the results. The graph below shows the results obtained by the learners. Okay, you can see that this is a direct proportion because it's a positive gradient passing through the origin, meaning as the square of the distance increases, also will the inverse of the force. Okay, great. So it says now use the graph to write down the relationship between the distance and the inverse of the force. Okay, that one is out. So write the relationship between there. Okay, the relationship between the inverse of the force and the distance between the charges. So that's easy. So we've got 6.1, 6.1.1. We know that this is the direct proportionality. Okay, that's the direct proportionality. And then we've got 6.1.2. It says determine the magnitude of charge in each sphere. So we've got to work out some things. First of all, we know that the electrostatic force is going to be K Q1 Q2 over R squared. This is Coulomb's law. Yeah? But now we know that these charges are the same. So this implies that when you take the inverse of the electrostatic force, it will be the inverse of the right hand side also. This is K Q. But now since these ones are the same, it's going to be KQ squared over R squared. Yeah? Great. Which also implies that 1 over the electrostatic force is, now this flips, it becomes now R squared over K times Q squared. So this is our equation. Please do show this. It's important, because without it we are lost. So this is the equation that governs the businesses here. Okay, so now what do we know? This is a variable. Just a moment. So we've got our variable R, and we can see here that the force is also a variable. So what is the constant here? So if we can just kind of modify our force here, this is Fe is equal to 1 over K Q squared times R squared. Okay, so this is important to notice, okay, that this is a constant, because K is the constant, the charge is the constant. So the variables are just these two. Okay, so obviously that becomes the gradient because it's a straight line graph. So that's the gradient. So what we're trying to arrive at is to say this implies that the gradient is equal to, now we want to put it out for everyone to see that that is the gradient. And you can see if we calculate the gradient, we know the constant, we don't know Q, so we can work out Q pretty easily. Okay, now the gradient is always a change of Y over change in X. So let's see, if we look here nicely, this one falls onto the line. So we can see that if we read it across, it's going to be 8, and then if we read it down, it's going to be 0.6. So we can use that because all those points are collinear. You don't want to be straining your head here trying to calculate the small ones. So the gradient is always change in Y. Now change in Y is going to be 8 minus 0, okay? Because we're taking it from the origin. This one is going to be 0.6 minus 0 is equal to 1 over kq squared. Maybe let's do this. Since we're substituting k, we know that it's 9 times 10 to the 9 into q squared. Okay, do we even need to write this thing? We don't. Okay, so that's what we've got. And then we do our famous gymnastics. Nice and easy. So this tells us that, therefore, our q is going to be equal to the square root Now remember, we were going to, sorry, let me see. This one will multiply there, right? Right. And then this one will multiply there. So this is basically going to be 0.6 divided by. Now this is 8 into 9 times 10 to the 9, right? So, yeah, that is the story. That is the story. So let's see, what do we get in there? What do we get? So this is the square root of 0.6 divided by 8 into 9 times 10 to the 9. So this one gives us a 2.89 times 10 to the minus 6 coulombs. So this is 2.89 microcoulombs. So this makes sense. At least it's something that we can accept. All right, so that is how you work this out. So sometimes you need to be smart because you have a lot of issues. So if you identify the gradient, which was our key factor, because knowing that we have a gradient on the graph, we could easily use that as our means to an end. Okay, so that's how we get those 6 marks. Of course, we know for a fact that to get this equation into this format is important. Okay, so this is a mark for me. And identifying the gradient is another mark for me. Okay, so 2 marks. And then working out the gradient using the graph, using those changes, is another mark for me. And we can simply say the rest of the substitution is another mark. So we've got how many marks here? 1, 2, 3, 4. Then the last one is the 5th mark. Okay, then maybe, just maybe, we can give a mark for the original formula. So this is how these 6 marks could be scored. Again, please consult the formal marking guidelines. They will give you a better understanding. Here, I'm just trying to pinpoint, possible areas for scoring marks so that as you answer many questions, you ensure that those areas are covered fully, because if you just show up with things we don't know where they come from, we will be in trouble. Okay, not a problem. So let's do 6.2. So 6.2 says, in the diagram below, point charge B has a charge of minus 6 nanocoulomb, and point charge A has an unknown charge. Okay, so we need to find out. Now charge A is 0.40 meters away from charge B, which we can see over here. And then point P is the point that is placed 0.15 meters away from point A. Okay, so which is this point right there. Okay, now it says the net electric field at point P due to point charges A and B is 6 times 10 to the exponent 5 newtons per coulomb to the left. So now what is going on here? There are 2 ways. If this is already a negative charge, Okay, it's already negative. So that means the electric field lines are going towards B, right? At point P. So this will be exerting a force towards itself from point P. And if this is going to the left, it already says to us that other charge should also be negative, but it must have a bigger magnitude than this one, because then it pulls the electric field towards itself. Okay, or at least the electric field strength is towards that charge. So this must be a negative charge as well for that to happen. Okay, great. So question says now, is sphere A positive or negative? Most definitely negative. So we know that to answer 6.2.1, we know that this is negative. Okay, so we get a mark and we smile. So 6.2.2, it says draw an electric field pattern between charges A and B. So we know that this charge is negative. No, this is charge A. And then we've got charge B. It's also negative. So we know that these field lines must not intersect, okay? So the key here is that they don't intersect. So there's plenty of ways to show this. Masingene pha. Hadikene ka mono ntate. So there we are. Yeah, there we are. So it doesn't matter really how these look, but all we know that the field lines go towards the center of a negative charge. Same story there. Okay, so that is essentially the story right there. Maybe, yeah, that's it. Maybe we can write our B and our A more visibly. Okay, that's it. 3 marks. I believe the field lines for this region where they don't overlap is a mark, and then we get a mark for each one, and then we get a mark for the type of field lines that are going towards the center. So probably that's how those 3 marks are arrived at. Again, consult the formal guidelines for exact areas of marks, because those who wrote this paper may want to know how they did and why they didn't get certain answers correct, even though they may have done the correct thing. Okay, it says now calculate the magnitude of charge on sphere A. Okay, again, see, these type of questions are always there. They will haunt you, even in grade 12. So you might as well master them now. Okay, so now we're going to use the electric field. So we know that the electric field net is going to be the electric field due to A plus the electric field due to B. Great. And then, of course, do indicate somewhere. We're choosing the direction to the left as positive, right? So this implies that the electric field net must be equal to, going to use the Coulomb's law here, is going to be QA over R squared plus, remember, for A it's going to the left, so we're going to say for B it must be going to the right because of the negative charge, so it's going to be minus K QB over R squared. This implies now we can substitute. We said to the left is positive, so this is 6 times 10 to the 5. equals 9 times 10 to the 9 QA. Okay, divide by, now the distance is there, it's just going to be 0.15 squared. Minus 9 times 10 to the 9 into this one, we're just going to ignore the sign at this point. 6 times 10 to the exponent. They said 9 nanocoulombs is to the minus 9. All divided by. Now this one is going to be basically 0.40 minus 0.15, and then we square that. Okay. Easy. So this implies that QA is going to be equal to, first of all, is going to be 6 times 10 to the 5, right, plus 9 times 10 to the 9 into 6 times 10 to the minus 9. All of that over all of that over this 0.40 minus 0.15 squared. Okay, now what do we need to do? We divide that whole thing by Coulomb's constant times 10 to the 9. Well, that's how we stripped A. So we can say therefore charge on sphere A is, remember it's a negative charge, so we need to make up for that one. Okay, let's do the things. 6 times 10 to the 5 plus 9 times 10 to the 9 into 6 times 10 to the minus 9, divide by 0.40 minus 0.15, that's squared. Okay, this is our first answer, and then that answer we divide by 9 times 10 to the 9, and then we get our answer here of 6 68 times 10 to the minus 5 coulombs. Okay, so obviously to the minus 5 is greater than to the minus 6, is it not? It is, so it makes sense. It makes perfect sense. No. Big problem. What happened to this guy? We lost it. So this can't be the answer. As very reassuring as it is, it means when we first transpose, we'll have to multiply this to that whole thing. So that 0.15 must be multiplied to the whole thing. Okay, so we start again. So 6 times 10 to the 5 plus 9 times 10 to the 9 into 6 times 10 to the minus 9, divide by 0.40 minus 0.15, that's squared. Then we get an answer, and then we multiply this answer by 0.15 squared first, and then we divide by 9 times 10 to the 9. So please guys, be very careful. Being vigilant is important. So I'm getting 1.50 times 10 to the minus 6 coulombs. Again, this microcoulomb is greater than a nanocoulomb, which makes sense, so we can accept the answer. We could have accepted the first answer, but be careful that all what you've got is representative in your final answer, or is represented instead. Okay, 6 marks, not a problem. We can simply say this substitution and that substitution, more especially that calculation, is important. And then the whole general substitution gives us now how many marks? 2, 4, right? And then we've got 5, so we can mark ourselves on this one. 6 marks in the bag, nice and easy. We're taking our 17 marks and we smile on. Okay, let's quickly do question 7. Maybe we can squash it here. Okay, so question 7 says consider a solenoid of 9 turns. Okay, so please take care of what you are given. 9 turns with unknown radius. Okay, once the radius is not known, it's a possibility that we may need to find it. Now the solenoid is subjected to a magnetic field of 0.12 Teslas. The face of the solenoid is perpendicular to the magnetic field. So this simply means if this is the solenoid, the face of the solenoid, okay, that is the solenoid there. So we know that this should be going stuff like that. Yeah, keba. So that is the solenoid. So I don't know why it's causing me a bit of discomfort now. Okay, there's the face. Now that means the magnetic field is hitting the solenoid at right angles. The face of the solenoid. It means that angle is 90 degrees. Okay, so this is the magnetic field lines. Okay, so technically, what is the story? The normal of the solenoid is also a perpendicular thingy that will hit the face at right angles. So it means the angle between the field lines and the normal of our solenoid is going to be equal to 0 degrees. So that is the story. So the key of that piece of information is to tell us that the angle between the field lines and the normal of that area of the solenoid is 0 degrees. Okay, so now it says when the field is uniformly switched to, so they are switching these things to 12 Teslas over a 2-minute period, an EMF of minus 0.3 volts is induced. Okay, so state Faraday's law of electromagnetic induction in words. Okay, so this is cool because it's again a textbook work that you should already know. So what do we know about this guy? He says the induced EMF, okay, in any closed circuit okay, the induced EMF in any closed circuit is equal to, right, the rate of change, okay, of the magnetic flux, okay, through the circuit, okay. Ay, tengele babhaleka kabi ngoku. Okay, so basically the induced EMF in any closed circuit is equal to the rate of change of the magnetic flux through that particular circuit. Okay, very easy. Again, if you want to remember this, you know that EMF is going to be equal to N times the change of phi over change of time. So that is the steward. So always have an equation in mind, then try to describe that equation easily if you forget the definition, but make sure your words are correct and everything is flowing properly. So 7.2, then we've got here, it says calculate, so 7.2.1, the change in the magnetic flux. Okay, so we know that easy, EMF is equal to N times delta phi over the change in time. Now we were told here this is minus 0,3 equals minus 9, because the tens are 9, times delta phi, which is what we want, over the time. Now 2 minutes is going to be 2 into 60, because there's 60 seconds in a minute, and we're doubling that. We can say therefore our delta phi, remember this is over 1, we do cross multiplication, it's going to be minus 0,3 into 2 times 60 divided by minus 9. Alright, so let's do it. The calculator says minus 0,3 into 2 times 60 divided by minus 9. That is a 4. Now what is the unit of measurement? It's Webers. Magnetic flux is measured in Webers. Okay, great. So an easy one. So technically formula is important, the correct substitution is important, and that calculation or conversion is important, and the answer. And remember, don't forget the unit of measurement, it's important. So 7.2.2. So we're told to calculate the radius of the solenoid. Easy. We know that the change of phi is basically the field lines or the magnetic field strength multiplied by the enclosed area through which those field lines are passing, times cos of theta, which is the angle between the normal of the area of that solenoid and the magnetic field lines, right? But of note is that in this situation here, we could see that the magnetic field strength was changed from 0,1 to 12. So that is what changed. So basically we can simply say here, this is the same as, I don't know why I am not doing the substitution here. So we got 4 here. So this is 12 minus the initial, which is 0,12. The area basically is going to be pi because it's circular, r squared, cos. Now the angle we established is going to be 0 degrees. So that is the most important. That is the most important. We can say therefore, or maybe let's say this implies that r squared is equal to 4 divided by pi into this business here. This is 12 minus 0,12 because cos of 0 is 1. So we can forget about that, or maybe we can include it just for fun. We can say therefore our r is going to be the square root of this business, 4 divided by this thing here, pi into 12 minus 0,12. Okay, let's find out square root of 4 divided by shift pi into 12 minus 0,12. So we're getting a 0,33 meters. Because all our distances here we must calculate in meters unless otherwise stated. So this is cool. So what do we have here? Formula, nice and easy, general substitution, but this calculation in particular is important, and the answer. The rest of the gymnastics is your own indaba. Please guys know that. The mathematical gymnastics is a must, but we're not rewarding for doing that, unless, honestly speaking, there is something magical about it. Then only then we would want to look at the result of those gymnastics. Okay, let's try and drill question 8, nice and easy. Just do it here. So question 8 says, the circuit below consists of a 4 ohm resistor and a 3 ohm resistor and an unknown resistor R. Again, that's a possible question. The potential difference across the battery is 12 volts. Okay, so this is what you would call the EMF. In grade 11, we don't do internal resistance, so never worry about it. Then an ammeter, a high resistance voltmeter, sometimes we call a negligible resistance voltmeter, not negligible, but infinite. Okay, infinite, to say it's so large that no current passes through. Okay, now 2 open switches S1 and S2 and a battery are connected as shown. The resistance of the battery and the wires is ignored, meaning it's so small that we don't have to worry about it. Great, so what do we know? We know that, guys, this is a cell. Okay, so this becomes the positive end of our cell, and that becomes the negative end of our cell. And you can see that this line is suggesting that there is a series of cells that are put in there to make up this battery. But in a nutshell, this becomes the negative end while that is the positive end. And we know that our conventional current comes out of the positive terminal, goes through the circuit. But because these switches are opened, the current will just go through and go through because those ones are closed. And then it will go through and back to the battery. Okay, so that is fine. At this point, this is what we've got. Now this says only switch S1 is closed. Okay, so now if we close S1, what happens to the current? It splits here into 2, and then it will pass through here. It never refluxes, it will go through there. It always goes where there's a complete circuit, because this creates a high resistance to not allow current to reflux. And then it goes through there, and then like that. And then here they come together and complete the circuit. Okay, great. So that's what we've got at the moment. So now it says the power dissipated by the 4 ohm resistor is 9 watt. Now it says calculate the potential difference across the 4 ohm resistor. So it's an easy 3-mark question. So we can handle that. So we've got 8.1, 8.1.1. We know that power is basically V squared over R. So if you don't remember this, use this generic one, which is power is VI. And then do some gymnastics to arrive at that one. So sometimes you may not have this one, but it's so convenient. So this implies the power is 9 equals V squared, which is what we want, over the resistance, it's a 4. This implies that V squared is going to be 9 times 4. Therefore, the V of the 4 ohm resistor is going to be the square root of 9 times 4, which is basically 6 ohms. So 6 volts, okay? So that would be 6 volts because that would be 36, and we're not going to take the negative version. So, formula, substitution, the answer must come with the unit of measurement. Please, I would mark someone down for not including the unit because I don't know what they're talking about if they just write a number. Even though I know the question says potential difference, but it's mandatory to add. This is where examiners need to be strict, but you find them being flexible here. And they're like, if the question said, you're not going to have to do this, but come on, this is where it is mandatory. But as for the other things, labels and stuff, as long as someone fully explains and accounts for those labels, they should be acceptable, irrespective of what the standards are. Anyhow, let's not make an argument right now. So 8.1.2 says, determine the ammeter reading. Okay, so we want the total current when switch S1 is closed. So basically, because we don't know that resistance, we cannot use that parallel connection. So what becomes our scapegoat is finding the potential difference across the 3 ohm resistor, because it receives the total current. Okay, so if we find this guy, we will essentially know how to determine the total current, because it technically receives the total current than those two which receive a split current. Okay, so let's go for it. The story is saying we know that the V total is going to be equal to the V across the 3 ohm resistor plus the V parallel. Okay, we're just going to say it that way. Does it work? Yeah, it should. So this implies that we've got 12 equals the V across the 3 ohm resistor, which is what we're interested in, plus now the V parallel is effectively the 6 volts, because the voltmeter across the 4 ohm is the same as the voltmeter across the other resistor because they're in parallel. So they share the same voltage but divide the current. So we can say, therefore, the voltmeter across the 3 ohm resistor is going to be 12 minus 6, which is basically 6 volts. We can say then, we know that V across the 3 ohm resistor is going to be the total current, because it receives the total current, times R. We don't worry about too many things. This one is 6, we calculated. The total current is what we want. The resistance is 3. You can say, therefore, our I tot what am I writing now? Oh, Lord, what is that? So therefore, our I tot, which is the ammeter reading, is equal to 6 over 3, which is equal to 2 amperes. So we can say, therefore, our A is equal to, because I said the ammeter reading is equal to 2 amperes. So 2 steps, we could see 4 marks, most likely we were expecting that. So what is important here is just the substitution here, because that was a means to an end. Formula, the correct answer substituted into the correct formula, and the final answer is how we score those 4 marks, nice and easy. So we've got 8.1.3. So it says now let's calculate the value of the unknown resistor. Okay, so this is easy. we know that we can use the total voltage. So we know that V tot is going to be I tot plus times the total resistance. Okay, great. This implies that 12 is equal to the total current we calculated is 2. Now R total is going to be the 3 ohms plus. Now this one is going to be a product of a sum, so this is 4R over 4 ohms plus that one. So this is cool. So we know that we can divide by 2 throughout. So this means 6 is equal to 3 plus 4R over 4 plus RD. Okay, great. So what do? We transpose the 3 there, so we get 3. Oops, space is not great here. Then we transpose the 3. 6 minus 3 is 8. 3 equals 4R over 4 plus R. And then now this is over 1. Do the gymnastics, we get 12 plus 3R equals 4R. So we rearrange and sort it out. When we transpose this to that side, it becomes minus, so it becomes R is equal to 12 ohms. Great. All right. So this one is correct. The correct substitution is correct, but this calculation on its own is important. Yeah. And then the final answer, because the rest of the gymnastics we are not interested, so maybe let's mark the substitution on the right to make up for those 5 marks. Great, let's move. 8.1.4 says now switch S1 is opened and switch S2 is closed. So we're opening this and then we're closing this one here. That means the current will split here at this point. So there's no current now passing through that segment. So the current is passing through here, bends here, and then passes through that resistor. Okay, this creates a high resistance, so there's no reflux of current. No problem. So that's what we've got. So the parallel connections now is those two in series against that one. Using the resistor calculated in 8.1.3, calculate the effective resistance of the circuit. Easy. So 8.1.4, we can say that R tot is going to be equal to the 3. I'm trying to think, guys. Is going to be this one. It's basically equal to R parallel. Maybe let's write it that way here. Because now all of these things are actually parallel. And then what do we know? We know that those ones are in series, so it's going to be 3 plus 4. That is product times 12, right? Over sum. So we've got 3 plus 4 plus 12. So it's very easy here. So we've got here 7 times 12 divide by 7 plus 12. So I'm getting a 4,42 to 2 decimal places ohms. So that is cool. So substitution and answer, because it's just 2 marks. All right, let's finish up, guys. We are almost done. So 8.2 says a motor labeled 1500 watt is used for an average of 3 hours per day. Okay, Now the cost of electricity is 2 rand 60 cents per kilowatt times hour. So now what is kilowatt times hour? It's energy, is it not? Because you know power is the rate at which work is done. Therefore, when you cross multiply, we know work is going to be power times time. So watt times time is energy. So basically we are charging per energy. We are charging per energy used or dissipated. Okay. All right. Okay. So let's see. Calculate the energy used by the motor for 3 hours per day in kilowatt times hour, as we could see there. Fine. We know that this is easy. Power is equal to the rate at which work is done. Okay, great. Now we want this one in kilowatt times hour. But now we've got this power of hours given to us in watts. So we've got to divide that by 1,000. So we're going to have here 1,500 over 8,000. We're already doing substitution and conversion at the same time. Is going to be equal to the work is capital letter W over, then we are given 3 hours, so this is as good as that. So we'll do some gymnastic there. You can say therefore the energy dissipated is going to be 3 into 1,500 over 8,000. So let's see what is that. So we've got 3 into 1,500 over 1,000. So we're getting here 4,5 kilowatts times hour. Okay, that's what we were asked, so we had to do it like that. So again here, how many marks? 2. Wow, that is strange. So basically this conversion is the most important in the final answer. The rest is your own indaba according to the stories. Okay, all right, okay. So let's just finish up, guys. We are almost in where we want to be. So this was supposed to be 8.2. Then we move. So we've got 8.2.2. Last question. It says now calculate the cost of electricity. So you'll always be asked this question, guys. It's usually the simplest. So don't fluff it. Calculate the cost of electricity to operate the motor for a month with 30 days. So we're going to have 30 days in that month. All right. So basically we know the energy per day. Okay, because in one day we only operate 3 hours. So that is 4,5 kilowatts times hour. But now we need to know how much energy do we dissipate per month. So we will know that the energy here for the month is going to be the energy that we get in one day. So basically it's going to be 4,5 multiplied by the number of days in which we're doing this. So it's going to be 30. So let's see, 4,5 times 30. So this gives us 135 kilowatts hour times hour. So in 30 days, that's what we're going to get. Now the amount that we pay per kilowatt times hour is 260. We can say this implies that the cost of electricity in terms of energy here is going to be the price, which is 2 rand 60. Then we multiply by the number of, the amount of energy we'll have used in that period, right? So we're going to say 135 times 2.60. It is basically going to be 351 rands. Not a problem. So guys, this is very easy. but they kind of hid the fact that you're going to need 2 steps here. But maybe there is a way of calculating in just 1 step. Either way, calculating the amount of energy for that whole 30 days and essentially getting the price for the entire month is the story. Okay guys, that's the end. I hope you liked the video. Otherwise, I will see you next time.